Hi students, I'm here to walk you through chapter 2 and to do some examples with you. So here we go. Okay, in chapter 2 we talk about organizing and summarizing data. So you have a data set, gigantic data set. What are you going to do with it? You have to figure out some way to kind of make it meaningful, give it some, give it some meaning so that people will understand what's going on with it, and put it in some kind of a tabular form or a graph. Our brains, just in general as human beings, work very well with that kind of format of information. So that's what we're going to talk about. So first off, let's define a frequency distribution. So a frequency distribution is categories and the number of observations in each category. So note here in 2.1, we are talking just qualitative data, okay? Just qualitative data. So remember, that's non-numeric data. It's non-numeric data. So in a frequency distribution in the qualitative case, the categories are some kind of a qualitative variable, okay? And then you also have the number of observations in each category. So those categories are called classes, and the number of observations in the categories are called frequencies. Okay, let's do an example. Okay, so here's a problem from our book. It's in 2.1, it's number 28. Here we have a phlebotomist who draws the blood of a random sample of 50 patients and determines their blood types as shown. Okay, so qualitative data, right? Non-numeric. So we have 4 categories here: O, B, AB, and A. So first thing we're going to do is set up our classes. So we might write class, or we might write blood type. And then in the qualitative case, there really isn't a set order that you can, that you have to put the classes in. You might put them in alphabetical order, say A, B, or no, that would be AB, right? B and O. Okay? And then you would put the frequencies. Okay, and in this case, you could just go through the data list and count the A's. So let's see, we've got 1, 2, 3, 4, 5, 6, et cetera, et cetera. And it turns out we have 18 A's, we have 4 ABs, we have 6 Bs, and we have 22 O's. And then you can go back and check by summing the data, and you should get the same number of frequencies as you have original data values. Okay? So that is a frequency distribution. Okay, whoops. Whoops. Okay, so now let's talk about a relative frequency distribution. So relative frequencies are the percentage or proportion of data that's in each category. So in the A's, we had 18. So we would take 18, divide by our total number of data values, which was 50, and we would get 0.36. So 36% of our data are A's, okay, blood type A. And then AB, we would take 4, divide by 50, and we get 0.08. So 8% of our data was ABs, and so on and so forth. So we have 12% in the B category, and we have 44% in the O category. And then again, you can check your relative frequencies by summing up. You should get 1 or 100%, okay? Which checks in this case. Now, sometimes you're going to get, when you add up your relative frequencies, you're going to get a tiny bit larger than 1.00. You might get 1.02, or you might get a tiny bit smaller. You might get 0.99 or something like that. And that's fine, given that most of the time you have to round your relative frequencies to the nearest percentage or whatever. Okay? So that is a relative frequency distribution. Okay, so there we go. Relative frequency distribution, the categories and classes, and the percent or proportion of observations in each category. And the relative frequencies are the proportion or percentage of data in each category. Okay, so a couple nice types of graphs that we like to use for qualitative data are bar graphs and pie charts. They're the two main types of graphs. So with bar graphs, you're going to have in a new color here. With bar graphs, you're going to have the categories on the horizontal axis, and you're going to have the frequencies on the vertical axis. Okay? Or you can actually swap that, have the categories on the vertical, frequencies on the horizontal, and that's fine too. We're going to talk about frequency, actually this should say frequency histograms, because the technical type of graph for a frequency distribution is called a frequency histogram. So in the qualitative case, a frequency histogram and a bar graph is really one and the same. A Pareto chart is where we arrange the bars in order of decreasing height. And a pie chart, so it's a bar graph with the bars in order. And technically, they're used in business applications and stuff like that. They're in order of decreasing magnitude, the bars, because you want to show causality. That's the whole point. Okay? And also, so it's just a type of a bar graph. And a pie chart is, we've all seen these, right? They're circles, and they've got pie shape. They're broken up into pie-shaped wedges, and each wedge has, oh, it looks like a sideways peace sign, doesn't it? Each pie piece has the proportion of data. The proportion of data in the data set is the proportion of circle that's taken up by that piece of pie. Okay, so we will try all these different types of graphs. Okay, so going back to the blood type data, first let's try a bar graph. So I hope you guys like this presentation because I'm really digging this technology. It's really awesome. Okay, so a bar graph for the blood type data. We're going to have a vertical axis for the frequencies, and we'll go ahead and put our categories on the horizontal axis. And those were blood types. And then over here, we're going to have our frequencies. Okay, and we'll give ourselves places for our A data, our AB data, our B data, and our O data. And if you look back at the data, the highest frequency in any of the classes was 22. So we'll scale our vertical axis accordingly. So we might do something like 5, 10, 15, 20, 25, something like that. Okay, and then we're going to go ahead. I'm going to get a new color here because I can. And then we go ahead and draw the bars with the height of the bar portraying the corresponding frequency. So we had 18 values in the A category, so we'll go up to 18. We had 4 in the AB. And you know, if you're doing this by hand, don't worry about it being super, perfect. Just so long as you can kind of tell what it is. In the B category, we had 6, so that would be a little bit above the 5 line. And in the O category, we had 22. So we're going to go all the way up. 22, yeah, that looks about right. And you have a bar 22 units high. Okay, so the height of each bar represents the frequency, again, in that category. Now, note that in the in the qualitative case, again, the categories can be arranged pretty much however you want them. There's no set way to arrange them in a regular bar graph, okay? Let's see, what else was I going to say? Oh, also notice that there are no, embellishments on the graph. You want it to be very clean and very straightforward, all right? The only case where you might put the number of, see, here we only have 5 units in between each chit mark on our vertical scale. So it's pretty easy to tell how high each bar is. If you had, say, on a vertical scale, you had, say, 100 to 200 to 300, something like that, and then, you had a bar like here, and at the end of the bar, you might see where they write 173 or something like that to give an exact number of items in that category. But in the case where we're only 5 units apart like this, it's really not necessary, okay? Whoops, okay, I'm gonna try to highlight this whole thing and grab it. A chunk. Isn't that the best thing ever? Okay, so next let's try a relative frequency. Let's try a Pareto chart. Okay, so now we've got a Pareto chart. Okay, so a Pareto chart, just like a bar chart or bar graph, except again, the categories are arranged in order of decreasing frequency. So again, you would label, we've got blood type. I have to remember to write slowly with this stylus because otherwise it leaves little gaps. It can't catch up. And in the case of our blood type data, our O would go first because it had the greatest frequency. Our A would be next. Our B would be third, and our AB would be last. Okay, and still we have the same number of frequencies. I'll abbreviate. Okay, so 5, 10, 15, 20, 25, something like that. Okay, So we had 22 in the O category. Again, let's do a 22. The A's were 18. The B's were 6. And the ABs were 4. Here we go. So it would look something like that. So again, that's a Pareto chart with the bars in order of decreasing magnitude. So you could furthermore extrapolate from this data. Let's assume that this sample of 50 individuals that had their blood drawn, let's say they're representative of the population in the area where this phlebotomist took the sample, okay? So if 36% of our sample has type A blood, then can we assume that 36% of the population has type A blood? And if 8% has type AB blood, then 8% of the population has type AB blood, and so on and so forth, okay? So again, if we can assume that that is a sample representative of the entire population, okay? Let's try a pie chart. So I'm gonna sweet. I'm getting better at that. Okay, so for here, this is really sweet. Look at this. I can draw a circle that doesn't look like a circle at all, and then it snaps it right to a circle. Isn't that the best thing ever? I love it. Okay, so for a pie chart or a pie graph, however, whatever you want to call it. You take the, first of all, you take the relative frequencies of, let's say, in the A group, we had 0.36. In the AB, we had 0.08. Running into my circle here. In the B, we had 12. And in the O, we had 0.44. Then you take each one to get the degrees of the circle. Degrees of circle. Okay. You multiply each relative frequency by 360 degrees. So 360 degrees takes you all the way around the circle. Okay? So what you're doing is saying, okay, if 36% of our data is A data, then 36% of our circle should be made up of A data. And if 8% is AB, then 8% of our circle should be B data, and so on and so forth. So you multiply each one by, each relative frequency by 360 degrees, and we get 130 degrees. That's our A data. We've got 29 degrees, and I just rounded to the nearest degree for our AB. 43 degrees for our B data, and 158 degrees for our O data. And then you can add those up if you want and see that they add to 360 degrees. And again, you might be a degree or two off. That's okay. Okay, so then to construct the pie chart, if 360 degrees is all the way around the circle, then halfway around the circle is 180, and a quarter of the way around the circle would be 90, okay? I'm going to switch colors. Okay, so let's say we start off on the, say, the positive x direction, all right? And if we swing around to get the A data, 130 degrees, then that would be, let's see, straight up would be 90 degrees. And then, so let's let me see, if I went straight up like this, that'd be approximately 90 degrees. And then if I look at the next quarter of the circle, which is another 90 degrees, okay? So if I have this first quadrant over in the upper right that's 90. So 130 minus 90, I need 40 degrees more. So 40 degrees is approximately half of another quadrant. It's approximately half of that total of 90, right? So I can just kind of go, okay, about half of that, and I'll erase my little chicken scratch here. And I'll call that 130 degrees, and that's our A data. Okay, and then do the same for the next category. Okay, we've got 29 degrees. So again, if we look at a quarter of the circle, like from the line where we left off to like here, that would be about 90 degrees. And 29 is about a third of that. So can we say something like that? And that would be our AB data. I'm going to go get my eraser, clean this up. And then again, let's start at the line we left off, and we need 43 degrees. So 43 again is about, okay, so if we have like that being half of, or that being our 90 relative to the line we left off on, 43 is going to be about half of that. So we can do, say, something like that. And that's our B data. And then I'm going to go back and clean this up. And the rest, the 158, is our O data. That kind of looks like a peace sign too. I'm all about peace today, I guess. So anyway, there's our pie chart of the blood type data. And it would generally, you know, the different pieces of the pie might be in different colors. But sometimes if people want a certain category to stand out, they'll make it brighter than the rest of the categories and things like that. So you have to kind of take that with a little bit of caution. Excel allows you to do a lot of fancy stuff with pie graphs, and you'll also be doing that in your labs. Okay? So that is a pie chart. Okay, let's proceed. Okay, 2.2. 2.2, we start getting into numeric data, okay? So in the quantitative case, discrete and continuous variables kind of go into different categories because there's different things that you can do with a discrete distribution versus a continuous distribution, okay? And so the corresponding graphs are a little different as well. So in the numeric or quantitative case, a frequency distribution can have categories of single numbers, which is the discrete case, or intervals, which is the continuous case, and then the number of observations in each category, which are the frequencies. The classes, again, are the single numbers or the intervals, okay? Here, in the numeric case, we have what are called lower and upper class limits. Lower class limits, the smallest numbers that can belong to a class. Upper class limits, the largest numbers that can belong to a class. And then class width is the difference between two consecutive upper or lower class limits, okay? And again, lower class limits, upper class limits, and class width are a little bit different in the discrete versus the continuous case. So let's take a look. Okay, here is some more data. This is from your book. This is in 2.2. It's number 35. Okay, and here we have some discrete data. This is the number of televisions in a household. So the number of, a researcher with AC Nielsen, which is a pretty large national organization, polling organization, wanted to determine the number of color televisions in households. So he conducted a survey of 40 randomly selected households and obtains the following data. So there is our sample size, 40. Okay, so let's say we want to organize this data. So, we look at it, it's not, it's not really telling us a whole lot in its raw form. So we want to organize it in a frequency distribution. So here are classes, and I'm going to change color again because I can. How about orange? So our classes are going to be the number of color TVs per household, per, how about if I put HH? Is that all right, household? And then the classes are going to be dependent on the data itself. So notice that our smallest number is 0, and our largest number is 5. So we're going to include our smallest number all the way up to our largest. 5 color TVs. Can you imagine? Who watches that much TV? I don't know. Okay, and then let's find our frequencies. Frequencies. Again, abbreviation. Okay, so you can go through again and just count the number of zeros, of which there are 1. Count the number of ones, 1, 2, 3, 4, and so on and so forth. And there is actually 14 ones. Count the number of 2s, there are also 14 2s. The number of 3s, there are 8 of those. And you might want to go back and verify for me. 2 4s and 1 5. And again, you can add those values up, make sure that they equal the original sample size of 40. And there is your frequency distribution. So again, if you want to make a relative frequency distribution, it works exactly the same as in the qualitative case. So you've got relative frequencies. Again, I'm going to abbreviate. No, maybe I'll write it out. Relative freaks. So again, you take the number 1, divide by 40, and I got to the nearest percent 0.03. Take the 14, divide by 40, you get 0.35 to the nearest percent, and you just do that all the way down the line. So next we have a 0.35, we have the 8 gives us a 0.20, the 2 a 0.05, and the 1 gives us a 0.03. Okay, so there's your relative frequency distribution. When I added all those up, I actually got 1.01. And again, that's okay. Whoops, I lost my page. The 1.01 is okay because I keep losing my page. I'm hitting the little page turning thing down there. So how about over here, 1.01? And that's okay because we rounded. So the fact that you don't come out to exactly 100% is okay. Alrighty, so hope that makes sense. Let's look at a frequency histogram in the discrete quantitative case. So to do that, I'm going to take all this stuff and trash it. Ba-chink. Man, I love that thing. Okay, so here is a frequency histogram. In the discrete quantitative case. Oh, you know what I wanted to point out to you? If you back up this tape and look at that frequency distribution again, note that the lower class limits and the upper class limits for a discrete frequency distribution are one and the same. And the class width would just be the difference between each class value. So the difference between 0 to 1 is 1. So the class width would be 1. 1 to 2, 1 unit. 2 to 3, 1 unit. 3 to 4, 1 unit. So the class width is 1 unit. Okay? So for a frequency histogram, let's get some hot pink going. We've got, okay, so we're going to have our frequencies on the vertical, our classes on the horizontal, and our classes are, and we can write down here, color TVs per household. Per household. And then vertically, our frequencies. And we will make room for, okay, so our smallest number of color TVs per household was 0, which I hope you remember, is right on top of the vertical axis. And that doesn't really bode well for the appearance of our graph. So we're going to move 0 in a little bit and put it like there. 1, 2, 3, 4, 5. But to let the reader know that we've done that, we're going to make a little notation right here on that horizontal axis, which shows that we've altered that horizontal axis in some way. Okay, that's a 2 right there. 2, there we go. Okay, so frequencies, again, look back at your data, and I see that the largest number in any category was 14. So you might do something like 5, 10, 15. 5, okay. 1 in the 0 category. That would be like that. 14 in the 1 category. Something like that. 14 in the 2 category. 8 in the 3 category. 2 in the 4 category. And 1 in the 5 category. So there is your, now note a huge difference here between bar graphs and histograms. With a bar graph, you want the bars separated because you want to show the contrast between the different categories. In the numeric case, the quantitative case, you want the bars right smack up against one another because you want to show the fluidity of the numbers, in this case, the number of color TVs. If you don't have, for example, if you don't have 0 color TVs, you have 1 color TV, or you have 2 color TVs, or you have 3 color TVs. And that those bars right up against one another show that there are no blank numbers in between the bars that we're not considering in our data or in our graph. Okay, so a real important point there. Alrighty, another thing we're going to want to pay attention to with numeric data is the shape of the graph. Okay, the shape of the graph. And as you can see here, this data tends to kind of pile up on the left side of the data, or on the left side of the horizontal scale, and taper off a bit over here on the right part. So we might say that that data has a slight right skew. So let's talk about the different data shapes for a moment. Actually, I'll just do it on this page. So I was going to go back and find a blank page, but oh well. Chunk. Okay, there we go. Okay, so the different shapes of distributions that I'm gonna require you to know. Okay. Shapes of distributions. Okay, and the first one of those is called uniform. So uniform data occurs about with the same greatest frequency all the way across. So it would be like if you randomly select the last digit of someone's phone number. You would expect all the values to occur with about the same greatest frequency. So a uniform distribution would look something like that in the discrete case, because you would have that bar kind of histogrammy appearance. And in the continuous case, a uniform distribution is going to be a smooth curve, but again, because the values all occur with the same greatest frequency, it's going to end up looking like just a big rectangle. It's not very interesting, but it is a legitimate distribution shape. Okay? Chunk. Whoops. Okay, the next shape that I want you to know is called symmetric. Whoops, my pen back. So symmetric is where the data piles up in the center and tapers off on the ends with about the same greatest frequency. So it would be something like this. You might have little gaps here where the frequency was 0, and that's okay. But you can see that it generally piles up in the center, and the tails, or the skinny parts out in the edges of the distribution, these guys are about the same height. So again, you have that pile up in the center and about the same frequency distribution within the tails, or the extreme ends. Okay, so in the discrete case, you would again have that histogrammy look, and in the continuous case, you would have a smooth curve. And that's actually the graph of the normal distribution, which we will study extensively starting in chapter 7. Okay? So again, discrete and continuous. So let's go to the next one. You'll see also in the book that there are a lot more distribution shapes than I will expect you to know. So, oops. There we go. So just pay attention to the ones that we're talking about here, okay? So also you're going to have skewed distributions. A distribution has a right skew. If the data piles up on the left-hand side and tapers off on the right, so the direction of the tail is the direction of the skew, okay? So let's say we have, here is some discrete data that has a skew. And again, you can have some areas of frequency 0, but let's say we come out here and we've got something that looks like that. So you can see that the data really piles up on the left, tapers off on the right, and again, the direction of the tail is the direction of the skew. Okay? In the continuous case, you would just have something like that. And there's a popular statistical distribution called the chi-square distribution. I don't think we're going to get there this semester, but it is a very popular right skewed, particularly distribution. And then consequently, we have a left skewed distribution. So the left skewed distribution piles up on the right-hand side, and the skew is to the left. So let's say there's our horizontal axis, and let's say you've got something that looks like that. So again, you can see that you've got that pile up on the right, taper off on the left, which gives you the left skew. So again, the direction of the skew is the part where the tail is. To the right, it would be the larger values. To the left would be the smaller values. The histogram-y type graph would be discrete data. A nice smooth curve, whoops, something like that would be continuous data. And if you think about it, the reason being is with continuous data, you've got infinitely many possible values, right? Even though you don't necessarily use them all. So if you put infinitely many of these little bars together, they would be so close together you wouldn't see the distinction between the top of each bar. Okay, they would just all smash together so closely the curve becomes smooth, and that's what the difference is with continuous versus discrete graphs. Yay! Okay, what's next? Okay, so here we are with continuous quantitative data. Okay, drink of water there. Okay, so here we have the following data represent the percentage of people without health insurance for the 50 states and the District of Columbia in 2006. So here our sample size is actually 51. The directions, again, this is in 2.2, the directions tell us, okay, so our class is going to be the percent uninsured, and then we're going to have our frequencies. So I'm going to put them kind of over here because I'm going to need some room here. Okay, here in this book, the author tells us where to get started with the interval case, because it can be kind of hard to determine where to start and how to put your distribution together. So in this case, he tells us to start with a lower class limit of 8 and have the classes be 2 units in width. So if you recall, class width is the difference between any consecutive upper or lower class limits. So if the width is 2, that means we would add 2 to get to the next lower class limit, which would give us a 10. Add 2 again, the lower class limit of the 3rd class would be 12. The lower class limit of the 4th class would be 14, and so on and so forth. 16, 18, 20, 22, and we're going to keep going until we have enough classes set up for all the data. So those are all the lower class limits. So these guys are all the lower class limits, okay? The upper class limits are going to be numbers that are up to but not including the lower class limit of the next class. Notice that our data has 1 decimal point, okay? So if we make our upper class limits as 1 decimal point, we should be able to get our data into each class. So smaller than the number 10 with 1 decimal place would be 9.9, okay? So again, as we leave the first class, the next 10th that would be added to 9.9 would give us 10, and we would move right into the 2nd class, okay? And we do the same all the way down the line. So the 2nd class is going to be up to 11.9. 3rd class starts at 12, goes up to 13.9. 4th class starts at 14, goes up to 15.9. and so on and so forth. 17.9, 19.9, 21.9, 23.9, and 25.9. Okay, so there's our classes, and all of these are our upper class limits. Okay, so on the left, your lower class limits, on your right, your upper class limits. And then again, the class width is the difference between any consecutive upper or lower class limit. Notice that wherever you go, there's 2 units difference. Okay? Frequencies. These are a little harder to discern than in the discrete case. You might want to make a tally and tally off the values, how many are in each category. But I ended up with 6 between 8 and 9.9, 11 between 10 and 11.9, 8 and another 8, 7, 4, 4, 2, and 1. Okay, so there are the corresponding frequencies for the quantitative interval class case of a frequency distribution. Okay? Remember that you can rewind this presentation back to any point you want and watch it repeatedly to get the information down. Okay? Now, if we wanted to make these relative frequencies, let me take the frequencies and junk them. And if, again, we wanted to make these relative freaks, then we would take the total number of data values, 51, and then take the number of data in each category and divide by 51 to get the relative frequency. So I got 0.18, and then the next category you divide 11 into 51. Again, the numerator there being the regular frequency, I got 22, and then you continue down the list. I got 16. It was interesting how this data turned out, this relative frequency distribution, because almost all the values required rounding up. So they were 5 or higher. A lot of them are actually right at 5. And so when I totaled up this data, I got 1.8, which is kind of unusual. But, you know, if you wanted it to be more accurate, you could always go back and pull the data out one more decimal place or something like that. But anyway, there's your relative frequency distribution for the quantitative continuous case. Okay, let's look at a graph of that data. Let's see, did I leave enough room on the next one? No. All right, let's go back. I think I'm going to get everything here. Oh, that'll work. So let's look at a frequency histogram. Okay, frequency histogram. In the continuous interval case. So frequency histogram, I'm going to write over the data a little bit here, which should be okay. So now you go back to your frequency distribution, and note that the data starts at 8. So instead of taking the numbers all, leaving this huge spot in the horizontal axis until you get to 8, again, we're going to alter that horizontal axis a little bit, and we're going to tell the reader, hey, we're starting here at 8. And then in the discrete case, recall that we put the number representing each category or class right underneath, right in the middle underneath each bar. In the continuous case, you want to go all the lower class limits. You don't want to put the decimal parts in here. So we start at 8, the next class starts at 10, and the next class starts at 12, and the next class starts at 14, and the next class at 16, and so on and so forth until, let's see, 22, and I think, oh, no, we have a couple more. I'm going to put a little bit more room out here. There's 24 and 26. And again, that's the percent uninsured. And then our vertical axis is frequency. And note for relative frequency, you're going to get the exact same shape of graph because it's the same data. The only thing that's going to change is your vertical scaling. Okay? Okay, so we had 6, oops, our highest frequency was 11, so we might go something like 2, 4, 6, 8, 10, 12. Come on. That's a weird 6, huh? It looks like a B. 8, 10, 12. There we go. How about if I... There we go. It looks a little bit more like a 6. There we go. A little bit better 4. Okay, so from 8 up to 10, we had 6 values. Let me get a new color. Okay, so there's our 6 values. 10 up to 12, we had 11 values. 12 up to but not including 14, we had 8 values. And actually we had the same for 14 up to 16. 7 for 16 up to but not including 18. 4 in the next 2 categories, 18 up to 20 and 20 up to 22. 2 from 22 up to 24, and 1 from 24 up to 26. So there's our frequency histogram. And again, bars together. We don't want to show contrast like in the qualitative case. We want to show that we've included all possible numbers from 8 up to 26, okay? And actually it's up to but not including 26. So there are no gaps in the horizontal axis in that range of data values. And yeah, it's a beautiful thing. So there's a frequency histogram. Now note though, one thing about a frequency distribution that is a little, especially with interval value classes, is that when you have the interval classes, let's go back and take a look at a few of them. So remember, our classes were 8 up to 9.9. That is a 9. There we go. And the next one was 10 up to 11.9, etc. And then the frequencies, we had 6 values in the first class, 11 values in the second class, so on and so forth. So one flaw of a frequency distribution is that we have, the data's been categorized, it's been tabulated, it helps us understand it. Notice that we have a nice right skewed distribution here, right? Piles up on the left, tapers off on the right. But a major flaw here is that all we know about these 6 data values is that they're somewhere in between 8 up to 9.9. We don't know if they're evenly distributed throughout that interval. We don't know if they're on the, primarily on the lower end or the upper end. And the same with the 11 values here. You kind of end up losing, quote, your data values because of those interval classes. So it definitely has its pros and its cons. Okay, let's talk about a remedy to that. So again, shape of the distribution is important because ultimately it's going to give us clues in how we can analyze the data. And a lot of those methods are very dependent on distribution shape. Okay, so just some rules of thumb about frequency distributions. Remember that each observation belongs to one and only one class, okay? So your classes can't overlap, and the ending of each class has got to pick up right, no, let me rephrase. The beginning of a subsequent class has to pick up right where the previous one left off, okay? No overlapping. And you have to include enough classes to include all of the data, okay? Sometimes you're going to get 0 frequencies, and that's okay. You still include those classes and leave them in there. You don't eliminate them. Use the same width for all classes, and an exception would be, say, on the higher end of your distribution, if you would have a whole bunch of blank classes just to pick up 1 or 2 extra data values. Like on our percent uninsured data, if, say, maybe there was one value that was a 50 or something like that, and we don't want to include all those empty classes to pick up that one data value. So our largest class might be 24 and above, something like that. And that's very common. And the rule of thumb in statistics is that we use between 5 and 20 classes. The reason being is that if you don't have enough data for 5 classes, you probably don't have enough to group. And if you have too much for 20 classes, then the data is still kind of unruly, and you probably want to make your classes wider so that each class just holds more data. Okay? And again, that's just kind of general. Okay, so we talked about frequency histograms and relative frequency histograms, and again, always drawn touching. That's really, really important. And remember, with a bar graph, and you will see examples in the My Math Lab, My Stat Lab, where bar graphs are drawn side to side. You're really not supposed to, really not a good idea. And again, let's start paying attention to shapes of distributions of numeric data. And again, in the qualitative case, not really much you can do with that, okay? Oh, I think I left that page for the frequency histograms. Oh, well. Okay, so the next type of graph that is a really good one for numeric data is called a stem and leaf plot. So you split the data in halves. Part is called the stem, part is called the leaf. You draw them about a vertical line. The stems are written only once per that digit. And each leaf actually represents the data value. So I'll show you what I mean. There's also something called a dot plot, which is a really, really simple plot. It's not used very often because it is so simple. But there are cases where, that's kind of okay. So with a dot plot, you just have a horizontal scale and say where each data value occurs. That's a 1, a 0, 1, a 2, whatever. You draw dots depicting a data value there, and if you get duplicates, you just stack them up. Okay? They're really simple. But you have to have just a limited range of data. And again, you don't want a gigantic data set either, so not that useful. In StatCrunch, I don't know why, but the dot plots are really bad. So I'm going to ask you to do them just so you know that they exist in there, but be ready because they're kind of not very good. And in 2.2, they talk a little bit about time series graphs, and I do not cover those either. Okay, so let's go to the next page and look at our next data set. Okay, so this is data set out of a data set out of the book. It's number 45 on, I forget what page, but it's in 2.2. And let's construct a stem and leaf graph, okay? So notice, let's take this first column of data, okay? We've got the 12, we've got the 32, we've got the 21, we've got the 59. So what we're going to do is break these data values in half, right down the middle. The left-hand side is going to represent the stems, and the right-hand side are going to represent the leaves. Okay, which we're then going to draw about a vertical line. Okay, so let me start. I'll start actually down here. And you would go smaller to larger, top to bottom. So in the case of like the 3, you want to write that as 03. So it has 2 places just like every other number here. And the 9 you're going to write as 09. Okay? So your smallest stem are the first digits or the tens place of each one of these, no, I'm sorry, the ones place of each one of these numbers. So we're going to write, we start at 0 to capture these guys. And then we're going to go up to 50, which is our largest tens place. So we would go, no wait, was that, no that's, yeah, that is tens place. Ones place would be, yeah, that is tens place. So the stem is the tens place in this case. So we have 0, 1, 2, 3, 4, and 5. Okay. And then, like the number 12, you're going to write the leaf to the right of the vertical line, 2. And then the number 32, you write the 2 to the right of the vertical line. 21, okay, the 2's already been written, so there's the 1. 59, there's the 5, there's the 9. Okay, let's go to the next column. 22, okay, so there's the 2, there's the other 2. 37, 3, 7. 32, 32. 16, 1, 6. Next column. 27, 27, 22, 36. So hopefully you're with me. So again, those stems are only written once, and each leaf represents a data value, and you can go back and read them. Let's finish up, and I'll show you what I mean. Let's see, where'd we leave off? The 36, okay. And in the fourth column, we've got 3, 31, 46, 30. Fifth column, 25, 11, 51, and 9. And in the last column, we've got 30, 16, 55, and 24. And there is our stem and leaf graph. Okay? But you don't want to leave it like this. Okay? First, let me address the deal about the going back and reading the data. Okay, so you can go back and know, okay, so here's the advantage that these guys have over frequency histograms or frequency distributions. Because you can go back and know the value of each data value. Check it out. So you've got a 0 and a 3, so that's the number 3. 0, 9, so you got 9. You've got 12, 16, 11, 16. 21, 22, 27, 27, 22, 25, 24. So you can go back and pull the original data set out of the graph. Okay? So technically what you want to do with the leaves is to put them in numeric order. So let's see what that would look like. So a stem and leaf in order, let's see, would be, here's our vertical line. We've got 0, 1, 2, 3, 4, 5. And putting the zeros in order, we would have a 3, then a 9. The ones in order, we would have a 1, a 2, a 6, and another 6. Putting the twos in order, we would have a 1, a 2, a 2, a 4, a 5, and 2 7s. So in this case, all of the data, as you can see, is in order, which makes it kind of nice. 2, 6, and a 7. 46 only had one value, and then we have a 1, a 5, and a 9. And notice here too, so that's how you would ultimately want your stem and leaf to look, with the leaves in order. So note here too that you stack all of those digits kind of column-wise stacked up. And all the second digits kind of column-wise stacked up, and so on and so forth. Because if you scrunch your leaf rows together or string them out differently than the other rows, you're not going to get a good sense of the shape of the distribution. Because if you turn the distribution now on its side, you can see that it kind of piles up in the center and tapers off with about the same frequency on each side. So we would call that data symmetric. Okay, and note that if you turn it sideways, tilting your head to your right shoulder, the 0 is on the left as it would be on a horizontal number line with the numbers increasing. Okay, so that is a stem and leaf graph. Yay! Okay, to show you a dot plot, I'm going to go back in our pages here a bit. So I'm going to go back to this data, the television data. We'll take this and put it in the trash. All right, and we'll make a dot plot of the television data. Okay. I want you guys to make sure and tell me if there's any colors I'm using that any of you cannot see properly. All right, that's really important to me. Okay, so for a dot plot, you're simply going to draw a horizontal line. And you know what? It's not so horizontal. Let me try it. Make that a little better. Okay, that's a little better. And you're going to start with, okay, number of TVs in the household. We had 0, 1, 2, 3, 4, and 5. And then we're going to put a dot for each frequency. We only had 1 0 there, and we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 ones. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 twos. We had 8 threes, 1, 2, 3, 4, 5, 6, 7, 8. We had 2 fours, 1, 2, and we had 1 5. So that's a dot plot. And you would line up, just like we did kind of in a stem and leaf, with those first columns kind of being of the digits lined up. You would do that also here. You would line up your first dots horizontally, your second dots horizontally, etc. I didn't do a very good job of that, but hopefully you get the point. Okay, so that is a dot plot. Okay, so let's go to the end. And in 2.3, we're going to have an online discussion about graphs gone bad. So what makes a graph, go wrong? All right, and I'll show you a couple instances or cases right here. And you can read about this in your textbook. One thing that can happen is that like really small differences in data can be stretched out to look really, really big. Like for example, if you've got like, say you're looking at data that is showing that kind of a trend and you kind of glance at it and you go, wow, that's really, that's really gigantic, that increase. But say you look over at the vertical scale and say maybe this is 14% and you have 15% and maybe 16%. And so when all the dust settles, this that looks like this huge difference is really only 2%, which may not make a difference really in the scope of things at all. So there, somebody is trying to get you to look at a small difference as a really big one. Okay, and note here, a lot of cases they will eliminate that little notation that tells you that part of the axis has been left out. And that can occur vertically or horizontally in the case of leaving out part of the axis. Okay? Another thing that can happen is when you have these cutesy little picture graphs. Okay, and there are quite a few of those in your book as well. So let's say there was one that was something about percentage of people playing soccer, and they show like this little bitty soccer ball that's supposed to represent going to go circular. Whoops, I'm trying to get this this little IntelliPen to work. So let me try one more time here. I want my soccer ball looking decent. Okay, so say they have this little bitty soccer ball and they say, here's how many were playing soccer in, soccer ball, however it looks. Here's how many people were playing soccer in 1996. And then they have this gigantic soccer ball. Boink. Oh, I love that. And they're going, okay, so this is how many people were playing soccer in 2006. But there really isn't any indication. I mean, what are we supposed to do? Compare the area of the circles, the height of the circles? There's really not much indication about what the differences of those circles imply. Okay? So not really a good graph. You see these a lot in USA Today, and you'll see in the text where the author writes here's a USA Today type graph. And I can tell he's kind of ribbing USA Today in that sense. So that's chapter 2. I hope you enjoyed it. Chapter 3, we're going to start using our graphing calculators a lot, so I hope you have it. I'm going to get an overhead projector set up here, and I will also show you how to do the calculations on your graphing calculator as I make a new presentation, okay? And I'll try to get it to you sooner than I got this one to you, but we've had glitches with the studio, and my tech guy, bless his heart, has been working very hard to try to alleviate them. Okay, so ta-ta for now.